Hi, this is Chet Douglas. I'm a principal software architect from Intel, and today I'd like to talk about additions to the Infiniband and RoCE RDMA specification that came out in a recent 1.5 update. So here we go. Share my screen. All right. So what I'm going to talk about is the update to the Infiniband and RoCE specification, and this is volume 1, release 1.5, and it was published on August 6th of this year. It's a fairly large document at 2,000 pages. It's like 22 different issues were addressed, and there's 57 new sections or features that have been added. And so I'm going to talk briefly about several of these changes, and the main one I'm really going to focus on are the memory placement extensions, because these are probably the largest addition of new features to this version of the spec. So we're going to talk about Infiniband speeds that were added, QoS and bandwidth enhancements, and some virtualization updates, and then we'll spend the majority of time talking about the memory placement extensions and what they're used for and how they work. Okay, so to support enhanced speeds, the specification added the new speeds for Infiniband NDR, which applies to RoCE as well as Infiniband. Since RoCE shares the same Ethernet physical and link layer, RoCE is fully supported by these changes as well. So this is what gets you to the 400 gigabits per second, and future speeds are through these additions to the spec. I'm not going to talk too much about these. Another change was added bandwidth enhancements for enhanced port arbiter. These are new minimum bandwidth setting capabilities and allow dynamic bandwidth increases. So traffic requiring low latency and low jitter, such as management time sync heartbeat protocol, could take advantage of these new additions. Virtual port QoS, so bandwidth sharing and rate limiting configurations for virtual ports, has been added on top of the standard and enhanced Infiniband port arbiter features that are there. And so what I really want to talk about today are the memory placement extensions. And through the rest of this presentation, I'm going to just refer to them as MPE. The memory placement extensions, while they're not specific to persistent memory, there are some specific parts in there that make it easier to use persistent memory with RDMA. And some of the motivation behind this is one, for performance reasons. So this little picture here shows a demonstration of a performance comparison between a RDMA interface connected to an SSD versus RDMA connected to persistent memory. And then actually this first one over here is TCP/IP based data movement with an SSD. So in each of these cases, we're moving 4K of data, and we're just looking at the round trip latency of a single request and how long it takes. And so in the TCP/IP world, right, a significant portion of the work is all done in software. And so this has like we measured a latency of 88 microseconds for this particular setup. If we use that same SSD with an RDMA connection, we get rid of basically the TCP/IP stack latency, and we get a significant improvement in performance there. But the real motivation is if you connect persistent memory up, and instead of the SSD, and you use persistent memory as the backing store, and you RDMA directly into persistent memory, you basically get like another improvement, another full 1x improvement or 10x improvement in latency here as we get rid of basically all of the software overhead, certainly all of the software overhead for moving the data. Yes, there's still software overhead to set it up, but the actual data movement here is all done basically in hardware. And so because persistent memory is persistent storage, but it's connected to the memory bus, we can take advantage of the fact that we can RDMA directly into it, and we can realize some significant latency improvements over the same kind of connection done with an SSD. And so this is a huge motivation to want to use persistent memory, certainly with RDMA. And a lot of what I'm going to talk about in connection with these memory placement extensions, I'll show some examples that are specific to persistent memory. But all of what I'm going to talk about applies to volatile memory as well. So anyway, that's the motivation from a performance perspective. With the advent of PMEM, storage is now connected directly to the memory subsystem and can be accessed using RDMA. And so this is more of my motivation problem statement here. The problem is that existing RDMA doesn't provide RDMA write or atomic reliability guarantees. In other words, if you're writing to persistent memory and you're using an RDMA write command, the completion of that write does not guarantee the data has reached remote host memory. And so this will be an issue we're going to have to deal with when we use RDMA with persistent memory. With pre 1.5 specification, the Infiniband specification, any guarantees that the data has reached the persistence domain must be implemented by an upper layer protocol. This requires interrupts, pipeline stalls, adding additional latency to the transaction, and may not be scalable. So prior to the memory placement extensions, you have to implement some sort of tricks and software basically to guarantee to make things persistent and give you the reliability guarantees, because stock RDMA is not going to provide that. All right, so here's kind of an example of it. The RDMA acknowledge and completion only guarantees the data has been successfully received and accepted by the remote HCA. It doesn't guarantee it's reached its remote host memory. So in my little picture here, an RDMA write comes in and a number of packets are sent across the wire to the responder HCA, and then those ACKs come back. But those ACKs tell you nothing about whether the write data has made it out of the HCA and into the memory, the final destination memory. So this will be an issue, right? This is going to be an issue for writing to persistent memory. The fact that that write completion doesn't tell you that the data has made it to its final store. And further guarantees are out of scope of the standard. So basically, this is what we're stuck with, right? This is how an RDMA write works, and we're not going to change how that works. And so there are other ways of doing this, of guaranteeing the data has been placed correctly, and that's usually done through platform-specific means. Special messaging, sending a send command with a list of locations to flush, and waking up software on the responder side and having it do the flushing for you, or maybe bypassing cache and using an RDMA read because of the pipeline ordering guarantees, using an RDMA read to flush previous writes. But these are platform-specific implementations, right? These are not part of the Infiniband spec. It's not part of the transport to provide any of these guarantees. So what can we do here? Well, so what we did is the memory placement extensions were added in the 1.5's Infiniband spec, and we added two new opcodes, two new commands. The first one is flush, and I'm going to go through some specific sequences and show you some examples of all of these, or both of these, I should say. But the first one is a flush command, and it basically flushes all previous writes to a specific region per queue pair. And so it doesn't affect writes on other queue pairs, but specifically the writes on this queue pair will be part of the scope for the flush. It provides acknowledgement that volatile writes have made it to what we call global observability, which is the point in time when the data is observable by software. It also provides acknowledgements that persistent memory writes have made it to the power fail-safe persistent domain. And I'll talk a little bit more about that as well. And it's a pipelined operation. I'll definitely spend some time explaining what that means. but essentially it means you can put the flush on the wire and put it into the NIC, put it in the wiki queue, and you can follow that immediately with other commands. And if the flush fails or there's something wrong with the flush, that flush command will break the connection, and you can safely pipeline this with other commands. And I'll talk more about that. I have an example of this. So the main two things it provides, right, are guarantees on when the data has been placed, essentially. One for global observability for use with volatile memory, and then one for persistent memory. The other command that was added is an atomic write, and this provides an aligned 8-byte atomically updated value, and then provides guarantees for the remote pointer updates have been made. And so before this, we really didn't have a guaranteed way in the transport to write an 8-byte pointer update and not have it affect things. And so, sorry, impromptu visitor. And so the atomic write command allows a NIC to basically do an 8-byte pointer update, and you don't have to worry about that update being torn, i.e. it's atomic. And both of these commands are fully supported by Infiniband and RoCE. All right, so what can we do with these? Well, so here's an example of what I'm going to call a synchronous log writing example, where a requester host application wishes to send an 8-byte pointer update to persistent memory on this responder system. But you only want to send that pointer update if the main blob of data that you're writing was written correctly first. So you want to write a blob of data to persistent memory. And once that data has been made persistent, is in the persistence domain, then you want to perform an atomic pointer update. And so this is the atomic pointer update is a common scheme used for synchronizing shared data across multiple nodes. And so I'm calling this a synchronous log writing example, and I'll talk more about some of the scenarios where these apply. And so in this example, and you can follow along in the little picture on the right side, but the host writes the RDMA, does an RDMA write of data, RDMA write 1, and then follows that with a flush command. So right after issuing the write, without waiting for the write completion, you put a flush command, queue that to the requester HCA, and then without waiting for the flush to complete, you immediately queue your atomic write command to the requester HCA. And because of the ordering rules and the way flush is designed and implemented, basically the flush command has to execute first and complete before the atomic write that follows would be executed. And so if the flush command doesn't complete, or there's an error, a problem with it, the flush command will break the connection and the atomic write won't actually execute. And so the ordering rules prevent the responder HCA from executing the atomic write until the previous flush is completed. And so this allows the requester host application to queue the RDMA write, flush, atomic write in a pipelined manner without waiting for any intermediate completions to occur, right? So you don't need an upper layer protocol. You don't need to queue up some work item to software and have it do some work for you. So boom, you get RDMA write, flush, atomic write on the wire, one right after the other with no stalls and no waiting. And this is what I mean by pipelined operations. All right, and I'm going to delve into some more examples here in a minute. Okay, so I kind of showed you a little example of the two new commands that were added and when you might use those. But let's look at a couple higher level use cases where this kind of sequence might be utilized. And so my first picture here is, my first scenario is a synchronous replication scenario where an application is writing to persistent memory on one system, but is really replicating that memory to, say, 4 systems. So I've got system 0, 1, 2, and 3 here that all are going to get a copy of the same data. And so this is often used in the cloud to replicate your data across multiple nodes, right? So that the data can be considered persistent and replicated and available for like highly available use. It's typically copied to more than one system. And so in this use case, picture that the application is writing to all four of these systems, but the application can't declare that the write was successful and complete until the write is completed on all four systems. So this is kind of a synchronous thing where you need to write to all four of them and wait for those writes to all complete on all four before the application is signaled that that write is completed. And then the application knows that that data is highly available and it's replicated on four different systems in this case. And the application can proceed then knowing that the data has been replicated. So being able to do pipelined operations and do a write followed by a flush, followed by another write, followed by another flush, write, flush, those kind of sequences like this, where you need to flush everything and make sure everything's been flushed to all the systems before you can proceed with the next write. Being able to accelerate that and not have an application have to have intermediate pipeline stalls waiting for these writes to complete is advantageous. So if the application can just put all these write and flush commands on the wire, queue them all up, and just let the NIC and the network handle the ordering, it removes a significant pipeline stalls that the application would see otherwise. Okay, my next example is synchronous log writing. So in this example, I'm sharing the same data amongst multiple different nodes, and perhaps those different nodes are going to do some work on that shared data. And so there's a lot of applications and databases that kind of fall into the synchronous log writing example. And I touched on it earlier. It's basically I'm going to write a blob of data to multiple machines, and then I'm going to update a log. It's like a delta log, a change log, an undo log. There's lots of different ways it can be done, but the log essentially describes the state of the data and the changes that have been made to the data over time. And so in this example, you write your data to both machines, to two machines, and you update the log on both machines. And when you update the log on this system one, that application gets notified that that log has been updated, and then it can act on that data. So it sees the log update, and then it realizes, oh, new data has been added, and then it can act on the data. And so the app one is waiting for that atomic write to occur, for that pointer update to occur, and then it's going to act on that pointer update, know that something has been added to the log, and then act on the data that was added. And so this is another example where being able to do a write, flush, atomic write, flush, atomic write, or those kind of sequences where, again, you could take advantage of the memory placement extensions to accelerate things and remove upper layer protocol pipeline stalls that an application would have to have to do this kind of sequence without the memory placement extensions. All right, so now I'm going to jump into a few more details on how flush works. And so these are a little build out animations here. So this is my memory placement extension initialization flow. And so I've got a requester node over here on the left and a responder node on the right with an RDMA network in between. And I have an application on both requester and responder, and I have, in this case, DRAM and a NIC, an RNIC, and then another RNIC on the responder side and persistent memory. So here's my setup. So at the beginning of time, we're going to allocate persistent memory buffer on the responder. And so the application is doing this directly with the responder RNIC. And it's going to allocate a memory buffer, and then it's going to register that memory with the responder HCA. So in this example, I'm going to tell it the address, the length. I'm going to say this is a persistent memory buffer, and we're going to use that later for that flush selector to decide whether you're flushing to global observability or to persistent memory. And then I also have a flushable indicator, which indicates whether flushing is allowed in this region. And that would be used by the responder HCA to do a quick check when the flush command comes in later and verify that that flush command is valid on this memory range. So this is standard RDMA kind of stuff. And what I'm suggesting here is some additional indicators added to the memory registration that we already have today. In response to this, the HCA sets up, internal context. It generates a handle, and it saves off the address range, length, and the attributes, PMEM and flushable in this example, and then returns a handle back to the application. In response to that, the application will share that handle with the requester application. The requester application is going to be the one that's going to be sending, the RDMA writes, RDMA flushes, and atomic writes. And so, like with other RDMA, typically with RDMA, that handle needs to be shared with the requester. Once the requester has that handle, it will use that handle in the RDMA packets that it generates. And that's how the responder HCA later will know what memory region you're talking to and what the attributes of that region are. All right, so this is kind of standard RDMA stuff at this point. So now we've set up the region and we shared the handle with the requester. All right, so now I wish to flush the global visibility. So in this case, I have a global visibility point. So again, this depends on your platform as to exactly where in the hardware pipeline this point is. I think typically it's when data gets pushed into LLC, lowest level cache. When it's, again, once the data is visible by software, that's basically considered the global visibility point. So what we're going to do is, so now we've written some data and to the global visibility point, and now we want to flush it and make sure that it's been flushed to that point. And so, so you write the data to the responder volatile memory. So here's my RDMA write. We send it across, right? The HCA looks it up and looks up the handle and says, oh, this is global visibility, and it's flushable. So I'm going to allow this, or I'm going to accept the write. And so in my sequence, I'm showing the write completion coming back, right? And then writes actually going from the NIC to the global visibility point. I'm really trying to emphasize the fact that that completion, that light blue arrows going back to the left to the application, don't tell you about whether the data has been is globally visible or not. And so naturally, the pipeline is probably already flushing this, is already moving this data to the final point. But the point is we don't know. We don't know where that data is. And so we follow it with a flush. And so in this example, the flush has the global visibility bit set, basically saying, hey, I'm trying to flush this stuff to global visibility, right? And in that case, so the HCA looks it up, says, oh, this is a flushable region. They're flushing to global visibility. I'll accept the flush. And that forces any writes in the pipeline into the global visibility point. And then once that completes, then you get the completion back. Now, I'm showing the global visibility point being different than the actual DRAM where the final resting place for the memory is. And so I'm assuming that they're not the same. They could be, but so while the data could be moving from the global visibility point to the DRAM, we've already returned the flush at that point. So remember, the flush is telling you, hey, the data is globally visible now. That's what the flush is telling you for this case. So now I'm going to show you the exact same example with PMEM. So in this case, we're going to write to persistent memory. And so we look it up and the handle says, oh, we're writing to PMEM and it's flushable. So again, the write completion tells you nothing about where that data is in flight. And so we're going to follow that with a flush. And in this case, the flush has the PMEM indicator set saying, flush this to persistent memory and give me a flush completion once that's happened. And so same thing, the HCA looks it up and says, okay, this is writing to PMEM. This is a PMEM region and it's flushable. I'm going to allow the flush command, and that forces any remaining writes out of the pipeline and into the PMEM point, wherever that point is in your platform, and then you get the completion back. So both of these cases rely on platform. There's a platform involvement here, right? Wherever that PMEM point is or that global visibility point is, you're relying on the platform to help provide some of these, to provide these guarantees. But the important part here for this discussion is that the transport now has mechanisms to allow, these things to be passed over the transport and remove the burden from the application to have to implement this in higher level software. All right, so now I'm going to kind of tie this together with an example of a synchronous log writing example where we're going to write some data, we're going to flush it, and then we're going to do an atomic write and update a pointer, a remote pointer. And so what I'm trying to show here is the pipeline nature of all of this and the fact that all of this stuff is going on, in parallel at the same time. And so we're going to write data. So I'm tying it all together here. We're going to write the data to the responder persistent memory, right? So we're going to start with our RDMA write, and we send that to the HCA. Now, the application, as soon as he's put that RDMA write on the Wookiee, the work queue entry for the requester HCA, he now immediately puts the flush command, queues that to the HCA as well. So that's the second arrow here, where a PMEM, where we're already putting the PMEM flush on the wire, right? We're already queuing that up to the requester. No stall at all. We haven't waited for anything at this point. So now the third thing we queue up is the atomic write. So immediately we do the write, the flush, and the atomic write. Now they're all queued up to the requester. And what's going on is, right, the actual RDMA write completion's already happened. And as that comes back, the HCA on the responder side starts the flush because those writes are complete. So because the flush was already queued, the responder can start working on that immediately. As soon as the writes are complete, it can handle the flush request. So now once that flush completes, it comes back. And as soon as the responder HCA puts that flush completion on the wire, flush response on the wire, it can go ahead and execute the atomic write. So as soon as the flush successfully completes, it works on the atomic write immediately. And then, writes are going on in the background here from the persistent memory point to the final PMEM destination. That's all handled by the platform. That's just naturally happening in the background. And so what you have now is you've done a write, a flush, and an atomic write, and the application didn't wait for anything. The application queued all three of those commands, one right after the other, to the requester HCA. And the requester responder HCA, the new opcodes and the ordering semantics of the new opcodes give you this effect where the responder NIC HCA is the one who ends up doing the waiting. That waiting that was over on the left side and the requester application was doing is now pushed to the right side, and the responder HCA is now doing the waiting. And it removes these pipeline stalls from the application on the left side. And that could be significant. All right, so let me talk. So that's really the meat of the memory placement extensions. The two commands that were added, that's really the heart of the main changes, I would say, to the 1.5 spec. And so, well, what's next? So there is more work going on, and future versions of the spec, we're considering a mechanism to extend the opcode domain. So right now we've kind of run out of opcodes, and we have a neat proposal on how we can easily extend that to provide more opcode space for future editions. And one of those future editions we're looking at and eyeing is a verify operation that would kind of fall in line with these other pipeline commands we've already added, and so allow you to do a verify of something that you've flushed and remove the burden of pulling that data across the network and having the application do it. And I'm going to show you an example of how that would work here in a second. And then there's continued integration of the extensions into the base document. So this originally started as the MPE started as an extension, a separate section of the doc, and now it's been folded into the main document. So there's, additional work in, I think just, cleaning that up and making sure that, that the spec is as clear and concise. All right, more information. So, the Infiniband Trade Association, here's the link to the spec. RDMA vendors, we're really encouraging them to consider implementing the MPE in your Infiniband and RoCE adapters. And RDMA users, consider, enhance these enhancements, and consider what you could do with these enhancements, and perhaps remove some software overhead and some additional software latency by taking advantage of this. All right, well, so that is the end of my session, and I wanted to thank you guys for joining, and hope you enjoyed the content, and really hope that you found some information useful in here. We wanted to kind of go over some of the importance of the memory placement extensions and why these would be useful for you. So thanks. Have a great day, and please rate the session and give us your feedback. Thank you.